let me tell you something that might change the way you see the world around you. Every building you've ever walked into, every road you've ever driven on, every bridge, every tunnel, every dam holding back a reservoir of drinking water, all of it traces back to someone, somewhere, thousands of years ago, stacking one stone on top of another and thinking, I bet I can do this better. That's where engineering begins, not in a textbook, not in a university lecture hall, but in the hands of someone solving a problem with whatever they had lying around. And the story of how we got from those first stacked stones to the world we live in now, honestly, it's one of the most fascinating stories humans have ever lived through. So, let's go back. Way back. And I mean way back, before written language, before metal tools, before anyone had even thought about the wheel. We're talking about a time when the most advanced technology on the planet was a sharpened rock. And yet, even then, people were engineering. They were shaping their environment, solving structural problems, figuring out how to make things that would last. They just didn't have a word for it yet. The earliest evidence we have of deliberate construction, not just finding a cave and sleeping in it, but actually building a shelter, goes back at least 400,000 years. There's a site in Terra Amata, near Nice in southern France, where archaeologists found what appear to be the post holes of oval huts. Imagine that. Someone, probably Homo erectus or an early archaic human, gathered branches, stuck them into the ground in a rough oval, bent them together at the top, and probably draped animal hides or vegetation over the frame. It's not the Parthenon. But here's the thing. It's engineering. It's someone understanding that a branch stuck vertically into the ground can support weight. That if you lean two branches against each other, they're stronger than either one alone. That's the basic principle behind every A-frame structure ever built, and it was figured out by someone who couldn't count past their own fingers. Now, for a long time, that's roughly where things stayed. Shelters were temporary, made from whatever was at hand: branches, bones, hides, packed earth. People were nomadic or semi-nomadic, following game, following the seasons. You don't invest a lot of engineering effort into a house you're going to abandon in 3 months. But then something changed, something enormous. And it happened around 10 to 12,000 years ago in a crescent-shaped stretch of fertile land arcing from modern-day Iraq through Syria and down into the Jordan Valley. You've probably heard it called the Fertile Crescent, and what happened there was the Neolithic Revolution, the shift from hunting and gathering to farming and settlement. Think about what that means for engineering. The moment you decide to stay in one place, everything changes. Suddenly, you need a permanent shelter, not a temporary one. You need storage for grain. You need walls to keep animals out or in. You need to manage water because your crops need it, and you can't just walk to the next river anymore. Settlement is basically a dare to the universe. I'm staying right here, and I'm going to make this spot work. And engineering is how you win that dare. One of the oldest known permanent settlements is Jericho, in the Jordan Valley, in what's now the West Bank. People were living there in something like a village by around 9000 BCE. And here's what's remarkable. By about 8000 BCE, they had built a stone wall around the settlement. A wall. Not a fence, not a hedge, but a genuine stone wall, roughly 3.5 meters tall, almost 2 meters thick at the base, with a circular stone tower attached to it that stood about 8.5 meters high. That tower had an internal staircase of 22 stone steps. Let that sink in for a moment. 8,000 years before the Common Era, that's 10,000 years ago. Someone designed and built a stone tower with an interior staircase. We're not entirely sure what it was for. Some archaeologists think it was defensive. Others think it had a ritual or astronomical purpose. There's a fascinating theory that the tower was positioned so that, on the summer solstice, the shadow of a nearby mountain would fall directly on it at sunset, which would make it a kind of monumental calendar. But whatever its purpose, the engineering is undeniable. Someone had to figure out how to cut and shape stones, how to stack them so they wouldn't collapse, how to create a spiral staircase inside a cylindrical tower. And they did all of this without metal tools, without mortar, without any written engineering tradition to draw on. They figured it out by trying things, watching what worked, and building on what they learned. And this is something I want you to hold on to as we go through this whole story, because it comes up again and again. The history of engineering is not a history of geniuses having sudden flashes of insight. It's a history of incremental learning, of trial and error, of one generation watching the previous generation's buildings crack and sag and fall down, and then doing it slightly differently. Engineering knowledge, for most of human history, was not written down. It was embodied. It lived in the hands and eyes of the people who did the work. A mason didn't read about the right way to lay a stone foundation. He learned it by watching his father or his master lay 1,000 foundations, and he learned to feel when the stone was seated right. That kind of knowledge is incredibly powerful and incredibly fragile. If a tradition of builders is disrupted by war, by famine, by plague, the knowledge can vanish in a single generation. And sometimes it did. But let's stay in the Neolithic for a while longer, because there's another site that deserves some attention, and it's one that genuinely shocked the archaeological world when it was discovered. It's called Göbekli Tepe, and it's in southeastern Turkey, on a hilltop about 15 kilometers northeast of the city of Şanlıurfa. A Kurdish shepherd noticed some oddly shaped stones sticking out of the ground in 1994, and when the German archaeologist Klaus Schmidt began excavating the site in 1995, what he found upended a lot of assumptions about what early humans were capable of. Göbekli Tepe dates to roughly 9,500 to 8,000 BCE, making it contemporary with or even older than the wall and tower at Jericho. But it's not a settlement. There are no houses, no storage buildings, no obvious signs of permanent habitation. Instead, it's a series of massive circular enclosures, each defined by T-shaped limestone pillars, some of them over 5 meters tall and weighing up to 10 tons. The pillars are carved with elaborate reliefs of animals: foxes, boars, cranes, snakes, scorpions, and some of them have stylized human arms and hands carved into their sides, as if each pillar is a giant, abstracted human figure. The whole complex appears to be ceremonial or ritual in nature. And here's the kicker. It was built by hunter-gatherers, not settled farmers, people who, as far as we can tell, had no permanent villages, no domesticated crops, no pottery, and no metal. And yet, they organized the labor, developed the quarrying techniques, and solved the engineering problems necessary to cut 10-ton pillars from bedrock, transport them uphill, and erect them in precise circular arrangements. How did they do it? Well, the quarry is on the same hilltop, about 100 meters from the main enclosures, which helps. They didn't have to move the stones very far. But even so, moving a 10-ton block of limestone with nothing but human muscle, wooden levers, and maybe rope made from plant fibers is a serious engineering challenge. You need to understand leverage. You need to understand how to create a stable path for dragging heavy loads. You need to coordinate dozens, maybe hundreds of workers. And you need to feed all those workers while they're doing this. which means someone had to organize a surplus of food, hunted game, gathered plants, to sustain a large labor force. Some researchers have actually argued that the need to feed the workers at Göbekli Tepe might have been one of the pressures that pushed people in that region toward agriculture. In other words, engineering ambition might have helped drive the invention of farming, rather than the other way around. That's a wild idea, and it's still debated. But it's a beautiful example of how engineering doesn't just respond to society. It shapes it. Now, I want to talk about something that might seem mundane compared to monumental stone pillars, but it's arguably more important to the history of engineering than any temple or tower. I'm talking about mud. Specifically, mud brick. Because while the people at Göbekli Tepe were carving limestone megaliths, other communities across the Fertile Crescent were figuring out something quieter but revolutionary. You could take mud, mix it with straw or chaff, press it into a mold, let it dry in the sun, and end up with a uniform, stackable building block that was far easier to work with than cut stone. The earliest mud bricks we know of date to around 7,500 BCE, from sites like Sayonu and Çatalhöyük in Turkey. Çatalhöyük is a particularly fascinating place. It was a large Neolithic settlement, occupied from roughly 7,500 to 5,700 BCE, and at its peak, it may have housed as many as 8,000 people, which made it one of the largest human settlements on Earth at the time. The houses were built from mud brick, packed tightly together with no streets between them. You entered your house through a hole in the roof, climbing down a ladder into the main living space. The roofs were flat and served as the walkways and public spaces of the settlement. Essentially, the whole town was one continuous building, and you walked across the rooftops to get anywhere. It's a completely alien urban layout by modern standards, but it worked. The shared walls provided structural support. Thermal mass kept the interiors cool in summer and warm in winter, and the lack of ground-level doors made the settlement surprisingly defensible. And here's a detail I love about Çatalhöyük. The houses were periodically demolished and rebuilt on top of themselves. When a house got old or damaged, the residents would partially knock it down, fill the interior with rubble, and build a new house on top of the old foundation. Over centuries, this created a mound, a tell, as archaeologists call it, that grew higher and higher. The layers of construction are like a geological record of building techniques, and you can actually trace how mud brick technology improved over time. Earlier bricks are rougher, more irregular. Later ones are more uniform, better dried, more consistently shaped. The builders were learning, generation by generation, how to make a better brick. And that slow, patient accumulation of practical knowledge, that's the engine that drives all of engineering history. So by about 7,000 BCE, you've got permanent settlements, mud brick construction, stone walls and towers, monumental ceremonial architecture, and the beginnings of organized labor for large building projects. And all of this is happening before the invention of writing, before the wheel, before bronze, before the plow. The foundations of engineering were laid by people whose names we will never know, working with tools we would barely recognize, solving problems through observation and persistence and a willingness to try something and see if it held up. And what's coming next? What happens when these small settlements start growing into something larger, when villages become towns and towns become cities, when the first true urban civilizations emerge in the river valleys of Mesopotamia and Egypt? That's when engineering goes from being a local craft to something that reshapes the entire landscape. Because once you have a city, you have problems that no village ever had to solve. You need to move water. You need to manage waste. You need roads and harbors and granaries that can feed tens of thousands of people. And you need buildings that don't just keep the rain out. You need buildings that project power, that tell everyone who sees them that this city, this civilization, is something extraordinary, something enduring. And that's exactly what starts to happen in the river valleys, starting around 4000 BCE, maybe a little earlier, in the land between two rivers, the Tigris and the Euphrates, in what we now call Mesopotamia, roughly modern-day Iraq. Now, here's the thing about river valleys. They give you two things that are absolutely essential for building a civilization. They give you water, obviously, and they give you silt, rich, fertile soil deposited by seasonal floods. And if you can figure out how to manage both of those things, how to channel the water where you need it and keep it away from where you don't, how to plant crops in that beautiful dark silt and harvest enough grain to feed not just your family, but thousands of families, well, then you've got something. You've got surplus. And surplus changes everything. Think about what happens when you have more food than your community can eat. For the first time in human history, not everyone has to be a farmer. Some people can specialize. Some people can become potters or weavers or metalworkers. Some people can become priests. Some people can become administrators, keeping track of who owns what and who owes what. And some people, and this is the part we care about tonight, some people can become full-time builders, engineers, in the truest sense, even if nobody called them that yet. The Sumerians, who settled in the southern part of Mesopotamia, were among the first to really figure this out. By around 3500 BCE, they had established some of the earliest true cities in human history. Uruk is probably the most famous. At its peak, around 3000 BCE, Uruk may have had a population of 40,000 people, maybe more. That's not a village. That's not even a town. That's a city, with all the engineering headaches that come with it. And the biggest headache, the one that defined Mesopotamian engineering for thousands of years, was water. Southern Mesopotamia is flat. It's hot. It doesn't rain much. The rivers flood, but they flood unpredictably, sometimes too much, sometimes not enough, and rarely at exactly the right time for your crops. So the Sumerians had to build an entire infrastructure of canals, levees, reservoirs, and irrigation ditches to tame those rivers and distribute water across their fields. And this isn't simple digging. This is systems engineering. You have to understand gradients, how much slope you need for water to flow in the right direction. You have to understand how to reinforce canal banks so they don't erode. You have to figure out how to regulate flow, how to open and close channels, how to prevent one farmer upstream from taking all the water before it reaches the farms downstream. That last problem, by the way, is a social engineering problem as much as a physical one, and it's probably one of the reasons centralized government emerged in the first place. Somebody had to be in charge of the water. The canals themselves were impressive pieces of work. Some of the major irrigation canals in Sumer stretched for kilometers, and they had to be maintained constantly. Silt builds up, banks collapse, weeds choke the channels. There's evidence that Sumerian cities organized massive labor crews, hundreds, maybe thousands of workers, for annual canal maintenance. It was backbreaking, unglamorous work, and it was absolutely the most important engineering activity in the entire civilization. If the canals failed, the crops failed. If the crops failed, the city starved. It's that simple. And here's something that's easy to overlook but really fascinating. The Sumerians didn't just move water horizontally through canals. They also had to deal with a problem that still plagues irrigated agriculture today: salinization. When you irrigate in a hot, dry climate, the water evaporates and leaves behind dissolved salts. Over years, over decades, the salt builds up in the soil until eventually the land becomes too salty to grow anything. There's evidence that Sumerian agricultural yields declined significantly over centuries, and some historians believe that salinization was a major factor in the eventual decline of Sumerian cities. They were, in a sense, engineering themselves into a corner, solving the immediate problem of water scarcity while slowly creating a longer-term problem they didn't fully understand. And that pattern, solving one engineering problem while inadvertently creating another, is something you see again and again throughout history. It's still happening today. But let's talk about what the Sumerians built above ground, because that's where things get really visually, well, I should say, conceptually striking. The ziggurat. You've probably heard the word. A ziggurat is a massive stepped pyramid, built from mud brick, rising up from the flat Mesopotamian plain like a manufactured mountain. The most famous one, the Great Ziggurat of Ur, was built around 2100 BCE by King Ur-Nammu, and even in its partially reconstructed state today, it's breathtaking. The base is roughly 64 meters by 45 meters, and it originally rose in 3 enormous terraced levels, with a temple to the moon god Nana at the very top. Now, here's what's clever about how they built it. Remember, they're working with mud brick, sun-dried clay bricks, the same basic material people had been using for thousands of years. But at this scale, mud brick has real problems. It's not waterproof. Rain soaks into it, and over time the bricks soften, swell, and crumble. In a massive structure like a ziggurat, water infiltration could be catastrophic. So the builders of the Ziggurat of Ur did something smart. They used a combination of sun-dried mud brick for the core, the bulk of the structure, and fired brick for the exterior facing. Fired brick that's been baked in a kiln, is much harder, much more water-resistant, and much more durable. But it's also much more expensive to produce because you need fuel for the kilns, so they used it strategically, only where it mattered most, on the outer skin where it would take the brunt of the weather. And they set those fired bricks in bitumen, natural asphalt that seeps up from the ground in parts of Mesopotamia. Bitumen is waterproof. It's basically ancient tar. So you've got a waterproof outer shell of kiln-fired bricks set in bitumen, protecting a massive core of cheaper sun-dried mud brick. That's not just building. That's engineering. That's thinking about materials, about cost, about failure modes, about long-term durability. And there's another detail that I love. The builders incorporated what appear to be drainage channels, holes or weep pipes, built into the structure to allow moisture that did penetrate the outer shell to escape rather than accumulate inside. They understood that you can't make something perfectly waterproof forever. Water will find a way in. So instead of just trying to keep it out, they also gave it a way out. That's a remarkably sophisticated approach to moisture management, and it's essentially the same principle behind the weep holes you'll find in modern brick construction. 4,000 years later, we're still using the same trick. The ziggurats also tell us something important about the relationship between engineering and power. These weren't practical structures in any obvious sense. You don't need a 100-foot-tall stepped pyramid to worship a god. You could build a perfectly good temple at ground level. But that's not the point, is it? The point is the spectacle. The point is that when you're a farmer working in the fields outside Ur, you look up and you see this colossal structure rising above everything else, gleaming in the sun, and you feel in your bones that the king who built that, the God who lives at the top of it, the civilization that produced it, is powerful beyond anything you could accomplish on your own. Monumental architecture is a technology of social control, and the Sumerians understood that intuitively. But let's shift our gaze now, because while all of this is happening in Mesopotamia, something equally remarkable is unfolding along the banks of another great river, about 1,000 miles to the west, Egypt, the Nile Valley. And if Mesopotamia is the story of managing unpredictable water in a flat landscape, Egypt is in some ways an easier water problem, but a much harder building problem. Because the Egyptians had access to something the Sumerians mostly didn't: stone. Lots and lots of stone. Limestone, sandstone, granite. And what they decided to do with that stone still takes your breath away. But before we get to the pyramids, and we will get to the pyramids, I promise, we need to talk about what came first. Because the Great Pyramid of Giza didn't just appear out of nowhere in 2560 BCE. It was the culmination of centuries of experimentation, of trial and error, of engineers figuring out what worked and what didn't, sometimes through catastrophic failure. And that progression, that slow climb from simple to extraordinary, is one of the most beautiful stories in all of engineering history. The earliest Egyptian tombs for important people were structures called mastabas, flat-topped rectangular buildings made of mud brick or sometimes stone, built over underground burial chambers. They're not flashy. They look like big benches, honestly. The word mastaba actually comes from the Arabic word for bench, but they represent the starting point, the baseline from which everything else evolved. The first real leap came around 2670 BCE, during the reign of Pharaoh Djoser, and it came because of one man, perhaps the first engineer in history whose name we actually know, Imhotep. Now, Imhotep was many things. He was a priest, a physician, an advisor to the pharaoh. Later generations would actually deify him. He became a god of medicine and architecture. But what he did at Saqqara, just south of modern Cairo, was revolutionary. He took the mastaba concept and started stacking. He built a mastaba, and then he built a slightly smaller one on top of it, and then another, and another, until he had created a stepped structure rising about 60 meters into the sky. The Step Pyramid of Djoser, the oldest monumental stone structure in the world. And here's what's really important about it. It wasn't just a bigger mastaba. Imhotep made a fundamental material shift, from mud brick to cut limestone. He figured out how to quarry stone blocks, transport them to the site, shape them, and stack them into a stable structure that was far taller and far more permanent than anything that had been built before. The blocks are relatively small compared to what would come later, and if you look closely at the construction, you can see that the builders were still thinking in mud brick terms. The stone blocks are laid in courses that lean slightly inward, the way you'd stack mud brick to keep it stable. They were applying old techniques to a new material, which is exactly what you'd expect from engineers working at the frontier of what's possible. You use what you know, and you adapt. But the step pyramid also revealed problems. Stone is heavier than mud brick. It transmits forces differently. The underground chambers beneath the pyramid show signs of structural distress, cracking, partial collapse. The engineers were learning in real time what stone could and couldn't do at this scale. And what came after Djoser is a fascinating sequence of experiments, some successful, some not, as Egyptian builders push toward the true smooth-sided pyramid. There's a pharaoh named Sneferu, who ruled about a century after Djoser. and Sneferu's building career is basically a master class in engineering iteration. He built at least 3 major pyramids, and each one tells you something about what the builders were figuring out. His first attempt at Meidum appears to have partially collapsed. The outer casing fell away, possibly because the foundation wasn't adequate or the angle was too steep. His second attempt at Dahshur is the famous bent pyramid, and you can actually see the moment the engineers changed their minds. The pyramid starts rising at a steep angle, about 54 degrees, and then partway up, the angle suddenly shifts to something much shallower, around 43 degrees. And the result is this strange, kinked profile. A pyramid that looks like it changed its mind halfway up, which is essentially what happened. The builders probably noticed cracking, settling, structural warning signs that told them the steep angle wasn't going to hold. So they adjusted. They reduced the slope, spread the load more gently, and finished the structure at a safer angle. And here's what I love about the bent pyramid. It's honest. It shows you the engineering process frozen in stone. Most of the time, when we look at ancient monuments, we see the polished final product. We see confidence and perfection. But the bent pyramid shows you doubt. It shows you a team of builders who were paying attention, who noticed something was going wrong, and who had the good sense to change course rather than push ahead and risk catastrophe. That's real engineering. That's what it actually looks like when people are solving problems they've never faced before. Now, Sneferu didn't stop there. That's the remarkable thing. He built a third pyramid, also at Dahshur, and this one is called the Red Pyramid because of the reddish hue of the limestone blocks, and the Red Pyramid is a triumph. It rises at a consistent angle of about 43 degrees, the same shallow angle that the bent pyramid switched to partway up. And it's smooth, it's stable, it's elegant. It's actually the first true smooth-sided pyramid ever completed. Think about what that means. Sneferu's builders took the lesson from the bent pyramid, applied it from the ground up, and got it right. 3 pyramids, 3 attempts, each one informed by the failures and compromises of the one before. That's iteration. That's how engineering actually advances. Not through sudden genius, but through building, failing, learning, and building again. And then, one generation later, comes the structure that most people picture when they hear the word pyramid. The Great Pyramid of Giza, built for Sneferu's son Khufu, around 2560 BCE. And this is where you have to just pause for a moment and appreciate the scale of what these people accomplished, because the numbers are staggering. The Great Pyramid originally stood about 481 feet tall, roughly the height of a modern 48-story building. Its base covers about 13 acres. It contains an estimated 2.3 million stone blocks, with an average weight of around 2.5 tons each. Though some of the granite blocks used in the internal chambers weigh 40, 50, even 80 tons. The base is level to within less than an inch across its entire footprint, which is over 750 feet on each side. The corners are almost perfectly right angles. The sides are aligned to the cardinal directions, north, south, east, west, with an accuracy that's frankly astonishing for any era, let alone 2560 BCE. So how did they do it? And this is one of those questions that has generated centuries of speculation. Some of it reasonable, some of it wildly not. But here's the thing. We actually know quite a lot about how the Great Pyramid was built, even if some details remain debated. The stone came primarily from quarries very close to the site. The main body of the pyramid is local limestone, cut from quarries just a few hundred meters away. The fine white limestone casing stones, the ones that originally gave the pyramid its smooth, gleaming exterior, came from quarries across the Nile at Tura, about 8 miles away. And the massive granite blocks used in the king's chamber and the relieving chambers above it were quarried at Aswan, nearly 600 miles to the south, and transported by river. Think about the logistics of that for a second. You're quarrying granite, one of the hardest stones there is, in Aswan. You're shaping blocks that weigh tens of tons. You're loading them onto boats, floating them down the Nile, unloading them, transporting them overland to the construction site, and then somehow raising them hundreds of feet into the air and placing them with precision. And you're doing all of this without iron tools, without wheels for heavy transport, without pulleys in the modern sense. The primary tools were copper chisels, dolerite pounding stones, wooden sledges, ramps, levers, and an extraordinary amount of organized human labor. The workforce itself is something we should talk about, because there's a persistent myth that the pyramids were built by slaves, and the evidence actually points in a different direction. Starting in the 1990s, archaeologist Mark Lehner and his team excavated a workers' village near the Giza plateau, and what they found was revealing. The workers were well fed. Their diet included cattle, sheep, and goat, which were expensive proteins. They received medical care. Healed bones show evidence of treatment. They were organized into crews with names. We know this from graffiti the workers left inside the pyramid itself. Team names like Friends of Khufu and Drunkards of Menkaura. These weren't slaves dragged to the site in chains. They were organized labor, likely a combination of permanent skilled workers and seasonal conscripts. Farmers who worked on the pyramid during the Nile's annual flood season, when their fields were underwater and agricultural work was impossible. It was a national project, something like a massive public works program, and the organizational infrastructure required to feed, house, and coordinate tens of thousands of workers is itself an engineering achievement that rivals the pyramid. Now, the construction technique. The most widely accepted theory involves ramps, some form of inclined surface that allowed workers to drag blocks upward as the pyramid grew. But the specific ramp design is debated. A single straight ramp running from ground level to the top would have to be enormously long to maintain a manageable slope, over a mile long, requiring almost as much material as the pyramid itself. That seems impractical. A spiral ramp wrapping around the exterior is another possibility, and it has some appeal, but it creates problems with surveying. You can't easily check the accuracy of the corners and edges if they're buried under a ramp. A more recent theory, proposed by the French architect Jean-Pierre Houdin, suggests an internal ramp, a spiral passage built inside the pyramid itself, which workers used to haul, can stack enormous weight on top of it, and it holds up beautifully. That's why pyramids work so well. Every block is being squeezed, pressed down by the weight above it, and stone loves that. But tension, pulling forces, stretching forces, that's a different story entirely. Stone is terrible in tension. Think about it this way. You can take a stone column, stack 10 more on top of it, and it'll stand there for thousands of years without complaint. But take a stone beam, support it at both ends, and hang a weight from the middle, and it'll crack. It'll snap. Because when you load a beam, the top surface gets compressed, pushed together, but the bottom surface gets stretched apart. It's being pulled. And stone just can't handle that. It has almost no tensile strength compared to its compressive strength. This is one of those fundamental material properties that shaped the entire history of architecture, and the Egyptian temple builders ran straight into it. Here's the practical consequence. If you're building a temple hall and you want to roof it with stone, you need to span the gap between your columns with stone lintels, horizontal beams. But because stone is so weak in tension, you can't span very far. The longer the beam, the more it bends under its own weight and the weight of the roof above, and the more tension develops on the bottom face, and eventually it cracks. So, what do? You put your columns closer together. And that's exactly what the Egyptians did, which is why when you walk into a place like the Great Hypostyle Hall at Qanat, you're surrounded by a forest of columns. There are 134 of them in that one hall alone, some of them nearly 70 feet tall, and they're packed remarkably close together. The central columns are only about 15 feet apart. That's not an aesthetic choice. I mean, it creates an incredible aesthetic effect. This dense, shadowy, overwhelming space where you can barely see from one end to the other. But the reason they're so close together is engineering. They had to be, because the stone architraves spanning between them could only reach so far before they'd fail. And think about what that means for the experience of being inside. You're in this vast enclosed space. The hypostyle hall covers about 54,000 square feet. But you can never really see all of it at once. The columns block your sight lines. Light comes in through clear-story windows high up where the central nave is taller than the side aisles, and it filters down in these dramatic shafts through the dimness. The priests who designed these spaces understood the psychological power of that. You feel small. You feel enclosed. You feel like you're in the presence of something immense and unknowable. And all of that comes, in a very real sense, from the tensile weakness of limestone. Now, the Egyptians weren't the only ancient builders who had to deal with this problem. The Greeks faced it too, and their solution was essentially the same. Lots of columns, relatively short spans. That's what gives Greek temples their characteristic look, all those closely spaced columns marching around the perimeter. It's called post and lintel construction, and it dominated monumental architecture for thousands of years, precisely because stone was the prestige building material, and stone can't span worth a damn. The real breakthroughs in spanning space, arches, vaults, domes, those would come later, and we'll get to those. But for now, let's stay with the Egyptians for a bit longer, because there's another piece of their engineering legacy that deserves attention, and it's one that people don't always think about when they think about ancient Egypt. Water. The Nile. The entire civilization existed because of the Nile's annual flood cycle, and managing that water was one of the longest-running engineering projects in human history. Every year, the river would rise, flood the surrounding valley, deposit a layer of rich silt, and then recede. That silt was the farmland. That cycle was the food supply. And the engineering challenge was to capture as much of that floodwater as possible, hold it on the fields long enough for the silt to settle and the soil to absorb the moisture, and then drain the excess back into the river before the next planting season. The system they developed is called basin irrigation, and it's beautifully simple in concept. You divide the floodplain into large basins, essentially flat fields enclosed by earthen dikes, and you build canals and sluice gates to control the flow of water in and out. When the flood comes, you open the upstream gates and let water fill the basins to a depth of maybe a meter or so. You leave it there for a month, 6 weeks. the silt settles out, the water soaks in, and then you drain the basins through downstream canals, and then you plant. What makes this impressive isn't any single piece of it. The dikes are just packed earth, the canals are hand-dug channels, the gates are simple wooden structures. What's impressive is the scale and the coordination. The entire Nile Valley, stretching hundreds of miles, was divided into these basins, and the system had to be maintained constantly. Every year, the flood would damage dikes, silt up canals, shift channels. Every year, thousands of laborers had to go out and repair everything before the next flood arrived. And it all had to be coordinated. You couldn't just manage your own basin in isolation, because water flowing into your basin affected your neighbor's basin downstream. This was systems engineering, really, the same kind of interconnected management challenge that the Mesopotamians dealt with, but on a grander scale and with a more forgiving river. The Nile's flood was remarkably predictable compared to the Tigris and Euphrates. It came at roughly the same time every year, rose to roughly the same height. Not exactly, of course. There were bad years, low floods that meant famine, high floods that overwhelmed the dikes. But on average, it was dependable enough to build a civilization around. And here's something worth noting. The Egyptians maintained this basin irrigation system for literally thousands of years. From the earliest dynasties all the way through the Roman period and beyond, without encountering the salinization problems that eventually crippled Mesopotamian agriculture. Remember that? The salt buildup in Mesopotamian soils that gradually poisoned the farmland. The Egyptians largely avoided it, and the reason is fascinating. It comes down to drainage. The Nile Valley has a natural slope away from the river toward the desert margins, which meant that water could drain through the soil and carry dissolved salts away from the root zone. Plus, the annual flooding essentially flushed the system every year. Fresh water coming in, soaking through, carrying salts down and away. It was a natural reset. The Mesopotamians didn't have that advantage. Their flat alluvial plain didn't drain well, and their irrigation systems brought water in but didn't always take the salt back out. Same basic technology, canals, dikes, managed flooding, but different geography, and that geographical difference meant one civilization could farm the same land for millennia while the other slowly degraded its own soil. It's a powerful reminder that engineering doesn't happen in a vacuum. The same solution can succeed brilliantly in one context and fail catastrophically in another. And the variable isn't the engineering, it's the environment. But let's shift our gaze now, because while Egypt was building temples and managing the Nile, something remarkable was happening on the other side of the Mediterranean. Actually, let me back up a little further than that. There's a whole engineering tradition that often gets overlooked in these kinds of narratives because it didn't leave behind massive stone monuments, and that's the engineering of the Bronze Age Mediterranean. The Minoans on Crete, the Mycenaeans on mainland Greece, and the various cultures that traded and competed across the Aegean and Eastern Mediterranean during the second millennium BCE. The Minoans are particularly interesting from an engineering standpoint. Their palace complex at Knossos, on the island of Crete, dating to roughly 1700 BCE in its final form, shows a level of sophistication in building services, the stuff inside the building, not just the structure. That's genuinely surprising for its age. They had a drainage system with fitted terracotta pipes, tapered so they could nest together, with joints sealed to prevent leakage. The pipes ran beneath the floors and carried both rainwater and wastewater away from the palace. They had light wells, Open shafts cut through multiple stories of the building to bring daylight and ventilation into interior rooms. And they had what appears to be a flushing water system connected to at least one latrine, using rainwater collected from the roofs and channeled through the building. Now, we should be careful not to over-romanticize this. The archaeological evidence is sometimes ambiguous, and early excavators like Arthur Evans had a tendency to reconstruct things in ways that reflected their own assumptions. But even the most conservative reading of the evidence shows that the Minoans were thinking about building services, water supply, drainage, ventilation, lighting, as integrated systems, not afterthoughts. And that's a significant conceptual step. Because up to this point, most of the engineering we've talked about has been structural. How do you stack stones? How do you build walls? How do you span gaps? The Minoans were asking a different kind of question. How do you make a building work as a living environment? How do you move water through it, air through it, light through it? These are the questions that would eventually lead to aqueducts, to hypocaust heating systems, to the whole Roman infrastructure revolution. But the Minoans were asking them remarkably early. Meanwhile, there's another engineering achievement from this general era and region that we should talk about, because it represents something genuinely new: the deliberate, planned engineering of a harbor. Ancient ports are older than the Bronze Age, of course. People had been pulling boats up on beaches and anchoring in natural harbors for thousands of years. But there's a difference between using a natural harbor and building one. And some of the earliest evidence we have of constructed harbor works, breakwaters, quays, artificial channels, comes from the Bronze Age Eastern Mediterranean. Places like Sidon and Byblos on the Lebanese coast, or the harbor at the Egyptian site of Wadi al-Jarf on the Red Sea, which dates all the way back to around 2600 BCE and was associated with the very pyramid building operations we talked about earlier. That harbor had a system of stone-built galleries for storing boats and supplies, and a long stone jetty extending into the water to create a sheltered anchorage. Maritime engineering, the engineering of harbors, ships, and navigation, is its own enormous story, and it runs parallel to everything else we've been talking about. But the culture that would take all of these threads, structural engineering, water management, urban planning, harbor construction, and weave them together into something unprecedented in scale and ambition, that culture was just beginning to stir in a marshy, unpromising little settlement on the banks of the Tiber River in central Italy. A settlement that, according to tradition, was founded in 753 BCE, though the archaeological reality is messier and older than that. A settlement called Roma. And the Romans are where ancient engineering truly hits a different gear entirely. Because the Romans weren't necessarily the most original engineers in the ancient world. They weren't always the first to invent something. What they were, and this is what makes them so extraordinary, was the civilization that figured out how to do things at scale, reliably, repeatedly, across enormous distances for centuries. They were systems engineers in a way that nobody before them had ever been, and arguably nobody after them would be again for well over 1,000 years. And the foundation of that, the literal foundation in many cases, was a material. A single material that changed everything. Concrete. Now, when I say concrete, you're probably picturing the gray stuff in modern sidewalks and parking garages. And Roman concrete was different from modern Portland cement concrete in important ways, but the basic idea is the same. You take some kind of white calcium-based bite, You mix it with water and aggregate, sand, gravel, rubble, and you get a material that starts as a thick paste you can pour or pack into any shape you want, and then it hardens into artificial stone. That's the magic. That's the whole game. Because suddenly, you're not limited by the shapes that nature gives you. You're not quarrying enormous blocks and dragging them across the desert. You're not constrained by the tensile weakness of stone beams that we talked about with the Egyptians, where you need a forest of columns to hold up a roof because stone can't span very far without cracking. Concrete lets you make curves. It lets you make arches. It lets you make vaults and domes. And arches and vaults change the structural game completely because they convert what would be bending forces, the kind that break stone beams, into compressive forces that flow smoothly down through the structure into the ground. Compression is what stone and concrete are good at. An arch is basically a way of making gravity work with you instead of against you. The Romans didn't invent the arch. Arches show up in Mesopotamian architecture, in Egyptian tombs, in Etruscan gates. But the Romans took the arch and made it the basis of an entire architectural and engineering system. They used arches everywhere, in bridges, in aqueducts, in sewers, in the substructures of buildings, stacked on top of each other, side by side, in long, repeating sequences. And the reason they could do that so effectively was the concrete. Here's what's really clever about Roman concrete specifically. The key ingredient, the thing that made it special, was a volcanic ash called pozzolana, named after the town of Pozzuoli near Naples, in the volcanic region around Mount Vesuvius. When you mix pozzolana with lime and water, you get a chemical reaction, a pozzolanic reaction, naturally, that produces a calcium aluminum silicate compound. And this compound has a remarkable property. It sets underwater. It gets harder when it's wet. Modern Portland cement can do this too, but the Romans figured it out more than 2,000 years ago, and it meant they could build in places and ways that would have been impossible otherwise. They could construct harbor foundations below the waterline. They could build aqueduct channels that would be perpetually wet. They could pour foundations in marshy ground. The Roman architect and engineer Vitruvius, writing in the 1st century BCE, specifically describes this property and recommends pozzolana for maritime works. He knew exactly what it could do. And here's something that still impresses modern materials scientists. Roman marine concrete, the stuff they poured into seawater to build harbor breakwaters, has in many cases gotten stronger over the last 2,000 years, not weaker. Researchers studying samples from places like the harbor at Caesarea Maritima, that's King Herod's massive artificial harbor on the coast of what's now Israel, built around 25 to 15 BCE, found that seawater seeping through the concrete actually triggered ongoing mineral growth within the material. A mineral called aluminum tobermarite crystallized in the concrete over centuries, reinforcing its internal structure. The Romans didn't understand the chemistry, of course. They just knew that this particular volcanic ash, mixed in these particular proportions, made stuff that lasted. Empirical knowledge, hard-won through trial and error, passed down through generations of builders. Sound familiar? It's the same pattern we've been tracing since those first stone toolmakers. But let's talk about what they built with it, because the structures are staggering. And the best place to start might be the aqueducts, because aqueducts show you Roman engineering thinking at its most characteristic, practical, systematic, and operating at a scale that's hard to wrap your head around. Rome needed water. By the height of the empire, The city had over 1 million residents, maybe more, and they all needed to drink, bathe, cook, wash, and flush away waste. The Romans were also culturally obsessed with bathing. The great public bathhouses were social centers, places where business was conducted and politics discussed, and those baths consumed enormous quantities of water. So the Romans built aqueducts. Not one, not two. 11 major aqueducts serving the city of Rome alone, built over a span of about 500 years. From the first one, the Aqua Appia, completed in 312 BCE, to the last, the Aqua Alexandrina, finished around 226 CE. Together, these 11 aqueducts delivered something in the neighborhood of 1 million cubic meters of water per day to the city. Per day. That's roughly 260 million gallons. Modern estimates vary, but even the conservative ones are astonishing. Now, here's the thing about aqueducts that people often get wrong. When you picture a Roman aqueduct, you probably picture those gorgeous stone arches marching across a valley. The Pont du Gard in southern France, maybe, which is the iconic image. And those arcaded bridges are real, and they're magnificent. The Pont du Gard stands about 49 meters tall, 3 tiers of arches, built around the middle of the 1st century CE, to carry the aqueduct serving the city of Nemausus, modern Nimes. It's one of the best preserved Roman structures anywhere, and it's a UNESCO World Heritage Site, and it absolutely deserves to be. But here's what people miss. The arched bridges were only a small fraction of any aqueduct's total length. The vast majority of a Roman aqueduct ran underground, in covered channels cut through earth or tunneled through rock. The Pont du Gard's aqueduct was about 50 kilometers long in total, and the arcaded bridge portion is only about 275 meters of that. The rest is buried channel, invisible, unglamorous, and absolutely critical. The engineering challenge of an aqueduct wasn't really about building pretty bridges. It was about maintaining a consistent, very gentle downward slope over enormous distances so that gravity, and only gravity, would keep the water flowing from the source to the city. No pumps, no pressurized pipes for the most part. Just a channel with a carefully calibrated gradient, typically something like 1 meter of drop for every 400 meters of horizontal distance, though it varied. That's a slope so gentle you couldn't detect it by eye, and maintaining that gradient meant the aqueduct's route had to follow the contours of the landscape with extraordinary precision. When a valley got in the way, you either went around it, adding kilometers to the route, or you bridged across it with arches. When a hill got in the way, you tunneled through it. The surveying required to plan these routes was remarkable. Roman surveyors used an instrument called a groma for laying out straight lines and right angles, and a chorobates, essentially a long, flat board with plumb lines and a water level, for establishing horizontal planes. Simple tools, but in skilled hands, capable of extraordinary accuracy. And think about what that means in practice. You're planning a channel that might run 50, 60, even 90 kilometers through rough terrain. The longest Roman aqueduct we know of served Constantinople and stretched something like 250 kilometers. And the total elevation drop over that entire distance might be only 100 meters or so. You have to get the slope right everywhere. If any section is too flat, the water pools and stagnates. If any section is too steep, the water flows too fast and erodes the channel lining. If you make an error and the channel actually goes uphill at any point, the water simply stops. There's no pump to push it over the hump. gravity is your only engine, and gravity doesn't forgive mistakes. The Roman engineer and administrator Sextus Julius Frontinus was appointed water commissioner of Rome, curator aquarum, in 97 CE, and he wrote a detailed treatise on the city's water supply system, the Aqueductu. It's one of the most valuable documents we have about Roman infrastructure, because Frontinus was a meticulous bureaucrat who cared about getting things right. He cataloged each aqueduct's source, length, capacity, and condition. He worried about leaks. He worried about illegal taps, people secretly connecting pipes to the public supply, which was apparently a constant problem. He worried about the maintenance crews and whether they were actually doing their jobs. Reading Frontinus, you realize that building the aqueduct was only half the challenge. Keeping it running, decade after decade, century after century, that was the real engineering achievement. It required institutional knowledge, dedicated maintenance organizations, reliable funding, and political will. Infrastructure isn't just a thing you build, it's a thing you maintain. And when the maintenance stops, when the empire contracts, when the budgets dry up, when the skilled workers disperse, the infrastructure fails, not dramatically, not all at once, but slowly, inevitably. Channels silt up, arches crack and aren't repaired, vegetation roots into the mortar, the water slows, then trickles, then stops, and a city that depended on 1 million cubic meters of water a day has to shrink to fit whatever its local springs and the Tiber can provide. That's exactly what happened to Rome in the centuries after the Western Empire's collapse. The population that had peaked at over 1 million fell to perhaps 30,000 by the early medieval period. The aqueducts went dry one by one. The great bathhouses closed. The fountains stopped flowing. And the engineering knowledge that had built and maintained all of it, that knowledge didn't vanish overnight, but it attenuated, scattered, became fragmented. The institutional framework that had made it possible simply dissolved. But we're getting ahead of ourselves. Before Rome fell, it built. And the aqueducts, as impressive as they are, were only one piece of the infrastructure system. Because the water had to go somewhere after it was used, and that meant sewers. Rome's Great Sewer, the Cloaca Maxima, is one of the oldest engineering structures in the city, originally constructed, according to tradition, during the reign of the Tarquin kings in the 6th century BCE, initially as an open drainage channel to drain the marshy valley that would become the Roman Forum. Over the centuries, it was enclosed, expanded, and lined with stone, becoming a massive vaulted tunnel that's still partially functional today, more than 2,500 years later. That's durability. That's engineering for the ages, quite literally. And the roads. We have to talk about the roads, because Roman roads might be the single most consequential engineering achievement of the ancient world in terms of their impact on everything that followed. The Roman road network at its peak comprised something like 400,000 kilometers of roads, of which about 80,000 kilometers were major paved highways. They connected every corner of an empire that stretched from Scotland to Syria, from the Atlantic coast of Portugal to the Euphrates River. And they weren't just paths beaten through the landscape. They were engineered structures, built in layers, a foundation of large stones, then smaller stones, then gravel, then a paved surface of fitted stone slabs, cambered so that rainwater would drain to the sides. They were straight wherever possible, because the Romans understood that the shortest distance between 2 points matters when you're moving legions and supply wagons across a continent. The Via Appia, begun in 312 BCE, the same year as the first aqueduct, which is probably not a coincidence, since both were initiated under the censor Appius Claudius Caecus, ran from Rome southeast to Capua and was later extended all the way to Brindisi on the Adriatic coast, a total distance of about 560 kilometers. And here's what's easy to miss about the roads. They weren't just military infrastructure, though that's how they started. They were economic infrastructure. They were communication infrastructure. They were the physical network that made the Roman Empire function as a single integrated system rather than a collection of disconnected provinces. Goods moved on those roads. Ideas moved on those roads. Administrative orders moved on those roads, carried by the cursus publicus, the imperial postal and transportation service, which maintained relay stations and fresh horses at regular intervals so that official messages could travel at remarkable speed, perhaps 75 kilometers a day under normal conditions, much more in emergencies. The roads made the empire governable, and when the roads deteriorated, governance deteriorated with them. But of all the structures the Romans built, the one that might best capture the full range of their engineering ambition, the one that makes you stand there with your mouth open even today, even after everything we've talked about, is a building. A single building in the center of Rome, completed around 125 CE under the Emperor Hadrian, though it was designed by someone whose name we may never know for certain. The building is the Pantheon, and it is, without exaggeration, one of the most extraordinary structures human beings have ever created. Let's talk about why. From the outside, the Pantheon doesn't look all that remarkable. You approach it through a conventional rectangular portico, 16 Corinthian columns of Egyptian granite, each about 12 meters tall, each weighing roughly 60 tons, quarried at Mons Claudianus in the eastern Egyptian desert and shipped across the Mediterranean. That alone is a logistical feat worth pausing over, but it's really just the entrance. You walk through the massive bronze doors, and then you step inside, and everything changes. Because the interior of the Pantheon is a single, vast, uninterrupted dome, the largest unreinforced concrete dome ever built, and it held that record for nearly 1,300 years until Brunelleschi figured out how to top it in Florence in the 15th century. The interior diameter is 43.3 meters. The height from the floor to the top of the dome is also 43.3 meters, which means if you imagined a perfect sphere sitting inside the building, it would just barely touch the floor. The geometry is deliberate. It's a statement. And the only source of natural light is a single circular opening at the very top of the dome, the oculus, about 9 meters across, completely open to the sky. When it rains, rain falls through that hole onto the slightly convex marble floor below, which has drainage channels cut into it. That's the building. That's the whole idea. And it's been standing there, essentially unchanged, for 1,900 years. Now, here's the thing about the Pantheon that makes it an engineering story, and not just an architectural one. That dome should not work. Or rather, it works. But only because the people who built it understood concrete in ways that were incredibly sophisticated, and they solved a series of structural problems that wouldn't be fully understood in mathematical terms for centuries. Think about what a dome is, structurally. It's essentially an arch rotated around a central axis. And like an arch, it converts loads into compression. The weight of the dome pushes downward and outward. But unlike a simple arch, a dome also generates hoop stresses, circumferential forces that run around the dome horizontally, like the hoops on a barrel. Near the top of a dome, these hoop stresses are compressive. The dome is squeezing itself together, But below a certain point, roughly where the dome's curvature passes about 52 degrees from the top, those hoop stresses become tensile. The dome starts trying to pull itself apart around its base. And concrete, as we talked about earlier, is strong in compression, but weak in tension. So the lower portion of a large concrete dome is the danger zone. That's where cracks want to form, meridional cracks running from top to bottom, the dome splitting open like a peeled orange. The builders of the Pantheon dealt with this in several ways, and every one of them is clever. First, they varied the thickness of the dome. At the base, the dome is about 6 meters thick. At the oculus, it's only about 1.5 meters. That puts more mass where you need structural strength and reduces the load at the top, where it would only add to the forces pushing outward. Second, and this is really elegant, they varied the concrete itself. The aggregate in the lower portions of the dome is heavy travertine and tufa. As you move higher, the aggregate gets progressively lighter. Brick fragments in the middle sections, and then, in the uppermost part of the dome, volcanic pumice. Pumice is so light it floats on water. So the top of the dome is made of a fundamentally different, lighter concrete than the bottom. The builders were grading the material by density to reduce the load where it mattered most. This is not something you stumble into. This is careful, deliberate engineering. Third, they used coffers, those deep square recesses you see on the interior surface of the dome. 5 rings of 28 coffers each. They look decorative, and they are, but they also reduce the weight of the dome significantly without proportionally reducing its structural depth. It's the same principle behind an I-beam or a waffle slab in modern construction. You remove material from where it's not doing structural work, and you keep it where it is. The coffers lighten the dome while maintaining its effective thickness along the ribs between them. And then there's the base. The dome sits on a cylindrical drum whose walls are about 6 meters thick, and those walls aren't solid. They contain a complex internal structure of relieving arches and voids, a kind of hidden skeleton that channels the dome's enormous outward thrust down into the foundations. The foundation itself is a ring of concrete about 7.3 meters wide and 4.5 meters deep. The whole system, dome, drum, foundation, works together as an integrated structural unit, each part designed to handle the specific forces acting on it. Here's what's really wild about all of this. The Romans didn't have structural analysis. They didn't have calculus. They didn't have finite element modeling. They couldn't calculate hoop stresses or draw force diagrams. Everything they knew about how domes behave, they knew from building domes, from experience, from watching what cracked and what didn't, from the accumulated trial and error of generations of builders. The Pantheon is the culmination of that empirical tradition. It's not the first Roman dome. There were smaller ones before it, in bath complexes and palace halls, each one a little bigger, each one teaching the builders something new. The Pantheon represents the moment when all of that accumulated knowledge came together in a single, audacious leap. And it almost seems like they knew they'd pushed to the limit, because nobody tried to build a bigger unreinforced concrete dome for over a millennium afterward. The knowledge of how to do it, the specific concrete recipes, the graded aggregates, the coffers, the internal relieving arches, all of that was lost when the Roman building tradition fragmented. Brunelleschi, when he finally surpassed the Pantheon's span with the dome of Florence Cathedral in 1436, had to invent an entirely different structural system to do it, using a double shell design with herringbone brickwork because he couldn't replicate what the Romans had done with concrete. He solved the same problem a different way, and even his dome is technically not unreinforced concrete, it's brick masonry. The Pantheon remains unique. So let's sit with that for a moment. A building completed around 125 CE, using a material whose chemistry wouldn't be scientifically understood for another 18 centuries, solving structural problems that wouldn't be mathematically described for another 15 centuries, and still standing, still functioning as a building. It's been in continuous use since it was built, first as a temple, then as a church, with its original dome intact. The concrete has some cracks. There are those meridional cracks we'd expect, running down from the oculus, but they stabilized centuries ago. The building found its equilibrium and stayed there. That's what Roman engineering looks like at its absolute peak. And it raises a question that's worth thinking about as you lie there. What does it mean to build something that lasts 2,000 years? Because most of what we build today isn't designed to last 2,000 years. Most of it isn't designed to last 200. Modern buildings have design lives of 50 to 100 years. Our concrete, Portland cement concrete, the stuff we use for everything, actually degrades over time. The steel reinforcement inside it corrodes, expands, cracks the concrete from within. Roman concrete, in many environments, gets stronger. We talked about that with the marine concrete at Caesarea Maritima, the aluminum tobermorite crystals growing in the presence of seawater. The Romans stumbled onto a material that improves with age, and we replaced it with one that doesn't. There's something humbling about that. But here's the broader point, and it's one that connects everything we've been talking about across this whole long story. Roman engineering wasn't just about individual brilliant structures. It was about systems, the aqueducts, the roads, the sewers, the harbors, the concrete, the arches, the domes. They all fit together. The roads moved the legions that conquered the provinces, that generated the tax revenue that paid for the aqueducts, that supplied the water that made the cities livable, that attracted the population that demanded the roads. It was a feedback loop, an integrated civilization scale system, and the engineering was the physical substrate that made it all possible. And when that system failed, when the political will to maintain the aqueducts evaporated, when the roads crumbled, when the knowledge of how to make pozzolanic concrete was lost, the whole thing came apart. Not overnight. It took centuries. But the trajectory was clear. Rome's population, which may have reached 1 million people at its peak, dropped to perhaps 20 or 30,000 by the 6th century. The city couldn't support more than that without the aqueducts. The engineering had been sustaining a population density that the local environment simply couldn't handle on its own. This is the lesson that echoes forward through everything that comes after Rome. Engineering doesn't just build things. It builds the conditions that make civilization possible at a given scale. And when the engineering fails, or more, precisely when the social, political, and economic systems that maintain the engineering fail, the scale of civilization contracts to match. Now, while Western Europe was working through what used to be called the Dark Ages, a term historians have mostly abandoned because it's misleading, but which captures something real about the loss of large-scale engineering capability in that particular region. Engineering knowledge didn't disappear from the world. It migrated. It evolved. It flourished in places that are sometimes overlooked in the Western-centric telling of this story. And one of those places, perhaps the most important one for the continuity of engineering knowledge, was the Islamic world. Starting in the 7th and 8th centuries, the rapid expansion of Islamic civilization created a vast territory stretching from Spain to Central Asia, and within that territory, something remarkable happened. Scholars in cities like Baghdad, Damascus, Cairo, and Cordoba didn't just preserve Greek and Roman texts. They translated them, critiqued them, extended them, and in many cases surpassed them. The Bait al-Hikmah, the House of Wisdom in Baghdad, founded in the early 9th century under the Abbasid caliphs, became one of the great intellectual centers of the medieval world. And the engineering that emerged from this tradition was extraordinary. Take water engineering, since we've been following that thread. In a civilization that spanned some of the most arid landscapes on Earth, moving and managing water wasn't just useful, it was existential. And the engineers of the Islamic world developed systems of remarkable sophistication. The Qanat, an underground water channel that taps into a water table at higher elevation and carries water by gravity through a gently sloping tunnel to where it's needed, sometimes over distances of tens of kilometers. This technology had ancient Persian origins, but Islamic engineers refined it, spread it across North Africa and into Spain, and built some of the most extensive Qanat networks the world had ever seen. The beauty of a Qanat is that because the channel is underground, evaporation losses are minimal. In a desert environment, that's everything. That single design choice, keeping the water underground, can mean the difference between a city that thrives and a city that dies. And some of these Qanats ran for extraordinary distances. There are Qanat systems in Iran that stretch 40 or 50 kilometers with vertical shafts sunk at regular intervals along the route, maybe every 20 or 30 meters, so that workers could dig the horizontal tunnel in segments and so that air could circulate during construction. Think about the surveying challenge alone. You're digging underground, in the dark, and you need to maintain a consistent, very gentle downward slope over tens of kilometers so that gravity does the work. Too steep and the water scours the tunnel walls and eventually collapses them. Too flat and the water pools and silts up. The grade had to be precise, sometimes as little as 1 in 1,000, meaning 1 meter of drop for every 1,000 meters of horizontal distance. And they achieved this without modern instruments, using plumb lines, leveling boards, and an intimate understanding of the local geology. Now, the Qanat is a beautiful example of what you might call appropriate technology, engineering that's perfectly matched to its environment. But Islamic engineers didn't stop at refining ancient systems. They innovated in ways that are genuinely astonishing. And one of the areas where this shows up most clearly is in mechanical engineering. And here's where we need to talk about a figure who deserves to be far more famous than he is. His name was Ismail al-Jazari, and he worked in the late 12th and early 13th centuries in what is now southeastern Turkey, in the Artukid court at Diyarbakir. In 1206, he completed a book. Its full title translates roughly as the Book of Knowledge of Ingenious Mechanical Devices, and it is one of the most remarkable engineering texts ever written. Al-Jazari didn't just describe his machines. He provided detailed instructions for how to build them with precise dimensions, material specifications, and assembly sequences. This wasn't theoretical. This was a practical engineering manual, and the machines it describes are extraordinary. He built elaborate water clocks, not simple, dripping vessels, but complex automated systems with feedback mechanisms. One of his most famous clocks, sometimes called the elephant clock, was a monumental timekeeping device that incorporated a perforated float in a water tank, a ball release mechanism, automated figures that moved on the hour, and components drawn from Indian, Egyptian, Greek, and Chinese traditions. It was, in a very real sense, a multicultural machine, and Al-Jazari was explicit about his debts to earlier traditions while also clear about what he had added. But here's the thing that really matters from an engineering standpoint. Al-Jazari is credited with some of the earliest known uses of the crankshaft, the mechanism that converts rotary motion into reciprocating motion, or vice versa. Think about what that means. Every piston engine you've ever encountered, from the engine in a car to the steam engines that powered the Industrial Revolution, relies on a crankshaft. Al-Jazari used a crank and connecting rod system in a water-raising machine, a twin-cylinder pump that could lift water to a considerable height. The pump used 2 cylinders with pistons, driven by a water wheel through a crank mechanism, and it included one-way valves, what we'd call check valves, to ensure the water flowed in only one direction. That's a remarkably sophisticated piece of engineering for any era, let alone the early 13th century. And Al-Jazari wasn't working in isolation. He was part of a broader tradition of mechanical engineering in the Islamic world that stretched back centuries. The Banu Musa brothers, working in 9th century Baghdad, had written their own Book of Ingenious Devices nearly 300 years earlier, describing around 100 mechanical devices, including automatic controls, trick vessels, and fountains. Some of their devices used what we'd now recognize as basic principles of pneumatics and hydraulics, the behavior of air and water under pressure. They described conical valves, float valves, and delay mechanisms. These are the ancestors of the control systems that run modern industrial processes, not in some vague metaphorical sense, in a direct, traceable, mechanical sense. A float valve in a 9th century Baghdad fountain works on exactly the same principle as the float valve in the tank behind your toilet. Water rises, the float rises with it, and at a certain level it closes a valve and stops the flow. When water drops, the float drops, the valve opens, and water flows again. That's a feedback control system. It's automatic regulation. And the Banu Musa brothers were building these things more than 1,000 years ago. So let's step back for a moment and think about what's happening here in the broader story of engineering. Because something important has shifted. In the earliest chapters of this story, the stone tools, the first irrigation channels, even the pyramids, engineering was primarily about materials and structures. How do you shape stone? How do you move earth? How do you stack blocks? The machines were simple: ramps, levers, rollers. The intelligence was in the organization, the logistics, the accumulated craft knowledge. But by the time we reach Al-Jazari and the Banu Musa brothers, engineering has expanded into a new domain. It's become about mechanisms, about converting one type of motion into another, about controlling the flow of fluids, about building machines that regulate themselves. This is a profound shift, and it's one that will eventually lead, centuries later, to the steam engine, the factory, and the entire industrial world. But the seeds are right here, in the workshops of Baghdad and Diyarbakir. And there's another dimension to Islamic engineering that's easy to miss if you're only looking at individual machines and buildings. It's the systems thinking, the way engineers in the Islamic world approach the design of entire cities and landscapes. Take Córdoba, in what is now southern Spain, during the 10th century under the Umayyad Caliphate. At its peak, Córdoba may have been the largest city in Europe, with a population that some estimates put at several 100,000, though the exact numbers are debated, and some scholars argue for lower figures. What's less debated is the infrastructure. The city had paved streets, public lighting using oil lamps, an extensive system of public baths, and sophisticated water supply and drainage networks. The Great Mosque of Córdoba, begun in the 8th century and expanded over the next 200 years, is an engineering marvel in its own right. A forest of over 800 columns supporting a system of double arches, the lower ones horseshoe-shaped and the upper ones semicircular, creating a structure that's both visually stunning and structurally clever. The double arch system raises the ceiling height without requiring impossibly tall columns. And the alternating red brick and white stone voussoirs aren't just decorative. They help distribute loads through the arch system. But what really gets me about Córdoba is the integration. The water systems, the sanitation, the lighting, the public spaces. These aren't isolated achievements. They're components of an engineered urban environment, designed and maintained as a coherent whole. And this is happening at a time when most European cities had essentially no organized sanitation, no public water supply, and streets that were, to put it politely, challenging. The contrast is stark, and it tells you something important about the relationship between engineering capability and the political and economic systems that support it. Córdoba could build and maintain these systems because it had the wealth, the administrative capacity, the educated workforce, and the institutional will to do so. When those things eroded, as they eventually did, with the fragmentation of the caliphate, the engineering capability eroded too. It's the same pattern we saw with Rome, isn't it? The engineering doesn't fail because the knowledge disappears overnight. It fails because the systems that sustain it, the tax base, the governance, the supply chains, the trained workforce, break down. And this brings us to something that I think is one of the most underappreciated engineering traditions in the ancient world, one that was developing simultaneously but largely independently on the other side of the planet. Because while Al-Jazari was building his ingenious mechanisms and Córdoba was shining as one of the great engineered cities of the medieval world, engineers in China and in the civilizations of the Americas were solving their own extraordinary problems in their own extraordinary ways. And the story of Chinese engineering, in particular, has a depth and continuity that's almost hard to comprehend. Consider just one example: iron and steel production. By the time of the Han Dynasty, around the 2nd century BCE, Chinese metallurgists had developed blast furnaces capable of producing cast iron on an industrial scale. This is roughly 1,500 years before Europe achieved the same capability. They were using double-acting piston bellows, powered by water wheels, to force air into their furnaces, reaching temperatures high enough to fully melt iron, rather than just softening it into a spongy bloom the way European smiths did for centuries. And by at least the 11th century, during the Song dynasty, Chinese engineers had developed processes for decarburizing cast iron to produce something very close to what we'd call steel. The scale of production was staggering. Some estimates suggest that by 1078, China was producing around 125,000 tons of iron per year, a figure that England wouldn't match until the early stages of the Industrial Revolution, 700 years later. Think about what that means for a moment. Every assumption you might have about technological progress being a steady westward march from Greece to Rome to Europe to the modern world, it just doesn't hold up. The reality is far more interesting, far more complicated, and far more humbling. Engineering knowledge has always been a global phenomenon, with multiple centers of innovation developing solutions in parallel, sometimes in contact with each other and sometimes in complete isolation. And the solutions they developed were shaped by local materials, local needs, local geography, and local traditions of knowledge in ways that make simple comparisons almost meaningless. Take the Americas. While we're talking about engineering traditions that deserve more attention, consider what was happening in Mesoamerica and South America. The Maya, between roughly the 3rd and 9th centuries CE, built cities with populations in the tens of thousands in tropical environments where water management was an existential challenge. At Tikal, In what is now Guatemala, engineers constructed elaborate reservoir systems that collected rainwater, channeled it through paved surfaces into storage tanks, and used sand filtration, actual sand filtration, to improve water quality. They did this without metal tools, without the wheel for transport, and without draft animals. The engineering was entirely based on stone, earth, plaster, and an incredibly sophisticated understanding of hydrology. And then there's the Inca road system, the Qhapaq, stretching over 30,000 kilometers through some of the most extreme terrain on Earth, coastal deserts, high mountain passes above 4,000 meters, and dense tropical forests. The engineering challenges were immense. In the mountains, the roads included stone-paved surfaces, drainage channels, retaining walls, tunnels cut through rock, and suspension bridges spanning deep gorges. The most famous of these bridges, like the one over the Apurimac River, were woven from plant fibers and could span distances of over 40 meters. They were rebuilt every year or two by local communities as a form of labor tax, which means the engineering knowledge wasn't locked up in a specialist class. It was distributed across the population, maintained through practice and tradition, renewed with each rebuilding. That's a completely different model of engineering knowledge management than anything we've seen in Rome or Baghdad, and in some ways it's remarkably resilient. The knowledge survives as long as the practice continues. And this is where something starts to crystallize, something about the nature of engineering knowledge itself that connects all of these traditions. The Roman concrete makers, the Islamic mechanicians, the Chinese metallurgists, the Inca bridge builders. In every case, the most critical knowledge wasn't written down in books. It lived in the hands and eyes and judgment of the people who did the work. Al-Jazari's book is exceptional precisely because it's exceptional, because most engineering knowledge in his era and in every era before the modern period was transmitted through apprenticeship, through watching and doing, through years of practice under the guidance of someone who already knew. And that kind of knowledge is powerful, but fragile. It can cross continents through trade and migration, but it can also vanish in a single generation if the chain of transmission breaks. Which brings us, finally, to the question of what happens when these traditions start to converge. When the engineering knowledge of the Islamic world begins to flow back into Europe, when Chinese innovations like gunpowder and the magnetic compass reach the West, when the slow accumulation of mechanical knowledge from 1,000 workshops and foundries begins to coalesce into something new, something that, for the first time, starts to look like what we'd recognize as the scientific method applied to engineering. And this convergence doesn't happen overnight. It's not a single moment or a single place. It's more like a slow tide, centuries in the making, fed by dozens of tributaries. But if you had to point to a region where the waters first began to mix in a way that would reshape everything, you'd probably point to the Iberian Peninsula, to Spain, and specifically to Toledo in the 12th century, because Toledo in the 1100s was one of the most extraordinary intellectual crossroads in human history. Here's the context. Toledo had been a Muslim-ruled city for centuries, part of Al-Andalus, that remarkable Islamic civilization on the Iberian Peninsula we talked about when we visited Córdoba. But in 1085, the Christian kingdom of Castile captured Toledo. And instead of destroying what they found, instead of burning the libraries, which is what happened in so many other conquests, the new rulers looked around at the vast collections of Arabic manuscripts and realized they were sitting on a treasure. These weren't just Islamic texts. They were Arabic translations of Greek works, Aristotle, Euclid, Ptolemy, Archimedes, Galen, texts that had been lost to Western Europe for centuries, preserved and expanded upon by scholars in Baghdad and Cordoba and Cairo. And alongside those translated Greek classics were original Arabic works on mathematics, astronomy, optics, medicine, and yes, engineering and mechanics. So what happened in Toledo was a massive, decades-long translation effort. Scholars, Christian, Jewish, and Muslim, often working together, translated these Arabic texts into Latin, the scholarly language of medieval Europe. And through those translations, an enormous body of knowledge suddenly became accessible to European thinkers who had been working with a fraction of the intellectual heritage that Islamic scholars had been building on for centuries. The works of the Banu Musa on pneumatics and clever devices. Al-Khwarizmi's algebra, the very word algebra, comes from the title of his book. Optical theories, astronomical tables, medical texts. It all flowed into European universities that were just beginning to form in places like Bologna and Paris and Oxford. Now, I want to be careful here, because there's a version of this story that treats it as though Europe was asleep for 1,000 years and then suddenly woke up when it received Islamic knowledge. And that's not quite right. Medieval Europe had its own engineering traditions. Cathedral builders, for instance, were doing extraordinary structural work, developing the pointed arch and the flying buttress and the ribbed vault, pushing stone construction to heights and spans that would have astonished the Romans. The great Gothic cathedrals, Chartres, Notre Dame, Amiens, these are engineering achievements of the highest order, developed through exactly the kind of embodied, master-to-apprentice knowledge transmission we've been talking about. The master masons who designed these buildings didn't have structural engineering textbooks. They had rules of thumb, geometric proportions passed down through guild traditions, and the accumulated lessons of buildings that had stood and buildings that had fallen. And sometimes they pushed too far. The choir vault of Beauvais Cathedral, completed in 1272, reached an astonishing 48 meters, the tallest Gothic vault ever built, and it partially collapsed 12 years later. They rebuilt it, added more supports, and it still stands today, but just barely, held together by iron tie rods added over the centuries. Beauvais is a monument to ambition outrunning understanding, and it's also a monument to the limits of purely empirical, trial-and-error engineering without the theoretical tools to predict when you've gone too far. And that's exactly what the influx of translated knowledge began to change. Not immediately. These things take generations. But gradually, European scholars now had access to Euclidean geometry, to Archimedean statics, to Arabic advances in mathematics. They had a theoretical framework they could begin to apply to practical problems. And this is the slow, quiet revolution that sets the stage for everything that comes after. Think about what that means. For all the traditions we've explored, Egyptian, Mesopotamian, Roman, Islamic, Chinese, Maya, Inca, engineering knowledge was primarily embodied. It lived in practice. The theoretical understanding, when it existed at all, was fragmentary, unsystematized, often disconnected from the people actually doing the building. Archimedes understood levers and buoyancy with mathematical precision, but Roman engineers built their aqueducts using practical surveying skills and rules of proportion, not Archimedean physics. Al-Jazari could build a pump with check valves that worked beautifully, but he didn't have a theoretical framework for fluid dynamics that would let him predict the performance of a pump he hadn't built yet. The knowledge was powerful, but it was specific. It told you what had worked before. It didn't give you reliable tools to predict what would work next. And this is the great transition that begins in the late medieval period and accelerates through the Renaissance. Engineering starts to become not just a craft, but a discipline that can be reasoned about abstractly, that can be taught through principles rather than only through practice. It doesn't happen all at once, and the old ways, the embodied knowledge, the apprenticeship traditions, remain essential for centuries. They're still essential today, honestly. No amount of textbook learning makes you a good welder or a skilled machinist. But the addition of theoretical tools to the engineer's toolkit changes the game fundamentally. Let me give you one beautiful example of this transition, because it's a story about a person, and it brings together so many threads. Filippo Brunelleschi. We met him earlier when we talked about the dome of Florence Cathedral. Remember, he solved a problem that had stumped everyone: how to build a dome spanning over 42 meters without the centering, the temporary wooden framework that conventional construction required. And the way he solved it was extraordinary. He studied Roman construction, almost certainly including the Pantheon. He invented new hoisting machines to lift materials to the working height. He devised the herringbone brickwork pattern that allowed each ring of the dome to be self-supporting during construction. He essentially invented the role of the architect-engineer as we understand it, someone who designs, plans, solves problems, and oversees construction as an integrated process. But here's what makes Brunelleschi a transitional figure in the deepest sense. He was trained as a goldsmith. His engineering knowledge was fundamentally embodied, learned through craft, through working with his hands, through observation and experiment. He didn't derive his dome solution from theoretical principles. He figured it out through a combination of studying ancient buildings, building physical models, and sheer creative problem-solving. And yet he operated in a world where theoretical knowledge was becoming increasingly available. He was a contemporary of Leon Battista Alberti, who wrote De Re Aedificatoria, the first major architectural treatise since Vitruvius, and one that attempted to ground building design in rational principles. Brunelleschi stands right at the hinge point between the old world of purely embodied engineering knowledge and the new world where theory and practice begin to intertwine. And after Brunelleschi comes Leonardo da Vinci, born in 1452, just 6 years after Brunelleschi died. And Leonardo takes this further. He fills notebooks with mechanical designs, with studies of forces, with observations about how water flows and how birds fly. He's trying to understand the principles behind the machines, not just build them. His notebooks are full of devices that would never work as drawn, but that's almost beside the point. What matters is the method, the attempt to reason about engineering problems from first principles, to sketch and analyze and iterate on paper before building in wood and metal. Leonardo couldn't have existed without the craft traditions that trained him, but he also couldn't have existed without the influx of theoretical knowledge, the geometry, the optics, the mechanics that the Great Translation movement had made available. So this is the convergence. Islamic mechanical knowledge, preserved and expanded Greek mathematics and physics, Chinese innovations in metallurgy and materials, European craft traditions in stone and timber. All of these streams flowing together, slowly, unevenly, with plenty of dead ends and lost knowledge along the way. And out of that convergence, over the next few centuries, comes something genuinely new. The idea that you can systematically study the natural world, derive mathematical principles from your observations, and then apply those principles to build things that have never existed before. That's the engineering revolution that eventually gives us the steam engine, the railroad, the suspension bridge, the airplane, the microchip. But all of it, every bit of it, rests on the foundation laid by the traditions we've been exploring tonight. And I think that's the thing I find most moving about this whole story when I step back and look at it, the sheer continuity of it. The fact that when a modern structural engineer calculates the load on a beam, they're using principles that trace back through centuries of accumulated understanding, through Galileo's studies of beam bending in the 1600s, back through the medieval master masons and their geometric rules, back through Roman concrete and Egyptian stone, all the way back to the first person who figured out that if you put a flat stone across two upright ones, you could make a doorway. That's one unbroken thread of human ingenuity stretching across 10,000 years. And the people. Think about the people. The unnamed Mesopotamian farmer who noticed that irrigated fields eventually turned white with salt and figured out that you had to let the land rest. Imhotep, stacking mastabas into the first pyramid and inventing monumental stone construction in the process. Sneferu's engineers watching the bent pyramid start to crack and making the gutsy decision to change the angle mid-build rather than watch it collapse. The Roman surveyor laying out an aqueduct grade of 1 in 5,000 across miles of rough terrain with nothing but chorobates and patience. Frontinus writing his treatise on aqueducts because he believed that public servants should actually understand the systems they managed. Imagine that. The anonymous genius who first mixed volcanic ash with lime and discovered pozzolanic concrete, the material that let Rome build an empire. Al-Jazari, spending 25 years documenting his mechanical creations with such care that we can still reconstruct them 800 years later. The Chinese ironworkers who figured out blast furnace technology 15 centuries before anyone in Europe. The Maya engineers who built sand filtration systems into their reservoirs without metal tools. The Inca communities who gathered every year or two to weave a new suspension bridge, carrying the knowledge in their hands and their traditions. Every single one of these people was solving problems. Real problems. How do we get water to our crops? How do we build something that won't fall down? How do we move goods across mountains? How do we keep a city clean? How do we span a river? They were working with whatever materials and knowledge they had, pushing against the limits of what was possible, sometimes failing spectacularly, and then getting up and trying again. And the knowledge they generated, through trial and error, through observation, through flashes of insight, through centuries of patient refinement, that knowledge didn't die with them. Most of it survived. It was passed on, hand to hand, master to apprentice, parent to child, book to reader, culture to culture. It accumulated. It grew. It became the foundation on which everything we have today is built. So the next time you turn on a faucet and clean water comes out, think about the Qanats. Think about the Roman aqueducts. Think about the Minoan pipes at Knossos. When you drive across a bridge, think about the Inca weavers and the Roman arch builders and the Gothic masons who figured out how to make stone fly. When you hold your phone, this impossibly complex device made of silicon and rare earth metals and glass, engineered to tolerances measured in nanometers, remember that it exists because 10,000 years ago, someone figured out how to shape a stone just so, and taught someone else how to do it, and that person taught someone else, and the chain never fully broke. That's the story of engineering, not the machines, not the buildings, not the roads or the domes or the dams, though all of those are wonderful. The real story is the knowledge and the people who carried it, the unbroken human impulse to look at the world, to understand how it works, and to reshape it, piece by piece, into something that makes life a little better, a little safer, a little more possible. And that story isn't over. It's still being written right now by engineers and builders and tinkerers and problem solvers all over the world. But for tonight, I think we've followed the thread far enough. The ancient engineers have carried us a long way, from the first shaped stones to the threshold of the modern world. And wherever you've drifted off along the way, that's perfectly fine. The knowledge will still be there in the morning. It's been waiting for 10,000 years. It can wait a little longer. So let yourself rest now. And if any of these stories stayed with you, the pyramids, the aqueducts, the dome, the bridges, let them settle in gently, like stones finding their place in an ancient wall, each one resting quietly on the ones below.